I'm going to go up to meshing, qubit cell size. And so it was the mapprops.spatialDB. So let's see. Let me go through the overview here. Oops. So what we're going to do is we're going to create, what qubit does is it can read in an Exodus file that has some field on it over its domain, and that field can be what cell size you want to use. So what we'll do is we'll create a mesh at a uniform resolution. Let me go back to, I probably never even brought up my slides. Here's my terminal. So there's, oh, whoops, that's Charles's. That's the wrong one. So there's where they are. And of course I've chosen to, yes, they work if you have the files. There was what, the geometry that we're going to do. So here's our cell size. So our first example was we're going to use a spatial database that you have not been provided to specify the cell size. And so we're going to base the cell size on some property in the spatial database. I think I used shear wave speed. And so we're going to make a uniform mesh within qubit. We're going to write out that mesh, and then we're going to use a Python script to add a field to that Exodus file. And so we're going to use our Python script to add in a cell size field to the Exodus file. Then we're going to read that file into qubit and use it to specify the discretization size. So this is sort of, it'd be very nice if we could just sort of read in a field into qubit, but the only way it can do it is through an Exodus file. And that Exodus file has to have exactly the same geometry as where we want to apply the field. So that's why we have to, and you can only do this cell sizing information with tets, tris, and quads. You can't do it with hexes because hexes, you can't take a structured grid and have it conform to an arbitrary spatial variation in cell size. You can do that for triangles, tets, and to some extent quads. So this is what our cell sizing function is going to look like. It's going to be, I think the shear wave speed varies just as a function of depth, and we're going to, that's very common to have a shear wave speed that varies as a function of depth. Stuff gets stiffer or softer near the surface. Stuff gets softer near the surface, stiffer with depth. So this is something that is very common, and then we're going to end up with a discretization that looks like this, where we have smaller cell size near the surface, and then it becomes bigger. Then the second case we're going to do, and then we're going to use the spatial database for that. The second case is we're going to use an analytical function. So we'll read in our Exodus file, and then we'll have some sort of analytical function as a function of space. So it could be like distance from the fault that specifies what the discretization size is. And so in this case, here's my cell field, my cell size function. So I'm going to be smaller in this region, and then as I get farther away from that region, I'm going to grow my discretization size. And Charles has done this sort of to create a more optimal mesh in 3D space when he knows sort of the distance from the fault. And in this case, this is what that mesh looks like. You'll see that I have finer discretization here, and then it's coarsening in a smooth way. So those are the slides for this case. And don't look at my debugging answer key there. So first, what we do is we run the journal mesh cell size journal. Then we're going to run a Python script that's called Exodus add properties. So it's going to read in the output, the Exodus file as output from there, add in these two fields, one for the analytical function, one for the spatial database function, and then we can run the other two journal files that, one uses the analytical function for the sizing function, one uses the spatial database for the sizing function. And so that was the read. Yeah, so there's a Python module that will provide an API for netCDF files. So that's what we're using. So let's see. So here's my geometry. I'll just, there's nothing particularly fancy about the geometry. I basically did a horizontal slice, then did a vertical slice, the upper part. And so let's see, I wanted mesh, so this first one, so I do the geometry, I do a uniform resolution of 4 kilometers, and then just export it. So there's my mesh, and that's what you saw in my in the slide diagram. So now let's see, where am I? So I'm going to go up to qubit cell size, and then I'm going to run this Exodus add properties. So let's look at what that file looks like. So here's the name of my mesh cell size.exo. Here's the name of the Exodus file. Here's my file name for the spatial database that's going to read in. Another parameter is the minimum period, so I'm going to make my cell size proportional to the minimum period of this. This is what I would use for a wave propagation. So I'm going to I made a really long wavelength. So here's the Python module netCDF4 that allows me to access the netCDF file. For generating the cell size using the database, here you can see in Python I'm importing spatial data information. I'm importing the Cartesian coordinate system, a simple database, simple IO ASCII. I do some initialization. I say I'm going to use a query type. I get my points, and then I tell it this is the spatial database. When I do the querying, this is the query interface. I open the database, tell it what value I want to query for, allocate the array to hold the result and the error flag, and then I tell it I'm going to query at multiple points. Here's the output. Here's the error flag output. Here's my points. Here's the coordinate system of those points. Then close the database. I extract VS. That's the value that I got out of the database, and then I'm going to make my cell size minimum period times the shear speed divided by 10. In this case, my minimum period is 10, so I'm basically saying the cell size is equal to the shear wave speed. If I wanted to resolve wave propagation at a period down to 4 seconds, I would replace this with my minimum period with 4 seconds, and this gives me 10 grid points per wavelength. Cell size analytical function. Here's my coordinates of a target, so I should just specify the coordinates of the location within the mesh. I compute a distance. I compute a bias factor, so I can use a bias factor of 1.05. Discretization at the start, and then this function here, as a function of distance, gives me the cell size that corresponds to the bias factor. So this is what qubit is doing internally when it's sort of walking down a curve now I'm doing it in 3D space in an analytical way. So these are the two functions I call to get the cell size given the list of points. Down here at the bottom, here's how I read the Exodus file. So I can say, okay, open up the Exodus file. I'm going to append to the Exodus file. Give me the coordinates variable, and then I pass on the coordinates variable to the grid size. Then I'm going to, within the Exodus file, I need to add in, need to tell it how many node variables I'm going to have. So I have, I'm going to add 2 node variables. I have to sort of allocate that, yes, what they are. So that's what these are doing. These are sort of net CDF4 manipulation of creating a variable. The strings for the variable names are like length 32 plus the terminating character. So it's HDF5 is a lot simpler than this. And then here's my create the variable. I'm passing it. So I have time step is 1, but that's because node variables in Exodus files may be associated with time steps, sort of like they are in output. Number of nodes. Here I'm assigning what the values are that go in there. So this is, this is all just what does an Exodus file version of a NetCDF look like? Where are the things stored? The things to be aware of is that, yes, I'm using a node variable, not a cell variable. You want to be using generally node variables for your discretization size, not cell variables. Other than that, it's pretty, I'm creating 2 variables, not just 1, because I wanted to just do one. I wanted one script to handle both cases. I think that's about it. I had to specify the time. And so that's what I ran. Now I go into my journal file. So let's open up cell size. We'll do the analytical function first. So the key here is, I need the exact same geometry. It's great that I have a geometry script so that I can just create the exact same geometry. If it takes a long time to create your geometry, like it did for the 3D subduction zone, you can create and save the qubit file and then reload that qubit file instead of playing back the geometry. So I'm going to do a TET mesh, and here's where things get fancy. Is that I'm going to import my sizing function from this other Exodus file for all blocks, and the name of the variable in there is cell size function, because that's my analytical function, and then the time stamp for that variable is 0. So what it's going to do now is it's imported the sizing function. So I say, then I have to tell it, okay, I've imported the sizing function. Now I want to apply that sizing function to the volumes and surfaces. So volume all sizing function type Exodus, because this is a field from an Exodus file, and the same thing with the surface. And so now it takes a little while, so it's reading in the mesh and it's associating the mesh with the geometry. And then curl all scheme stride, that just is the default. And so first I mesh the surfaces. And so now I have the surfaces, and then I'm going to smooth them to improve the quality there. So because I brought in a sizing function, I wasn't quite sure how smooth my sizing function was. So I meshed the surfaces first, smooth them to improve, make sure that they didn't have any sharp gradients and too sharp a gradients in cell size. Smooth my surfaces, and then I'll mesh the volume from there. And so it took 1 second to do the mesh volume. So it actually does pretty fast, even this arbitrary discretization size. If you have a really big, the bigger your sizing function mesh, the longer it will take, because it has to find things in there. Here I haven't changed my apropos lined beginning characters. Here I'm doing a loop to improve the mesh quality, so you can get a little fancier. And so I start out at a smoothing for a condition number 2, and then I crank it down 1.9, 1.8, 1.7, doing a loop of 4 times. If you try and crank down and say smooth to a condition number of 1.5, it generally won't give you a good quality mesh. You sort of want to trim your worst elements, your very worst elements, trim, smooth that really sort of zeroes in on the very worst elements, then slowly creep down your condition number smoothing. You'll end up with a better mesh that way. And so here I'm doing the condition number smoothing, cranking through 4 times. I do the cleanup with the tets as well. That helps sort of deal with sort of the mesh cleanup. If you get into sort of a jam where it can't smooth it, and smoothing will not do any reconnection. And so if you really improve the mesh quality by flipping a connectivity, an edge here or there, that's what the cleanup volume all for a tet mesh does. And then I'll write it out. So that's an analytical function. The case for the spatial database, essentially it looks the same in terms of what the mesh is doing. Again, sizing function, I tell it the name of the access file. I tell it the name of the variable, in this case cellsize dB, tell it the time, sizing function type Exodus. So let's just run that one. So it's doing the smoothing. Took a little long there for that last iteration. But you can see I have I can do a hidden line view. You can see I have a finer discretization size near the surface than I do at depth. Any questions? It is using the cell sizing function. I have no way of showing you what the interior of the mesh looks like, but it does use the cell sizing function. It's not. This is it doesn't show the interior. I think it's because in OpenGL, it's basically used to showing just the boundary surfaces, and they don't. I could, if I brought this into to ParaView, I could then sort of use some.
Oh, if you did edges only in ParaView, if you threw out the line, you can fit the edge over, then you can see them.
Yeah.
That's what I usually do. It doesn't have that.
Qubit does not have that capability.
So you can look at the mesh with the transparency on it.
Yeah. I mean, you can look on the side and sort of see, and you can sort of see, well, you probably can't. Oops. I mean, you can sort of see that interior surface. Oops. I want to get out of this.
It would be nice if you could just turn on one of the blocks.
Well, I can do. So did I create blocks? Well, you can't, I can do a block, but it's not much better than, there you can sort of see well, I mean, I have still a surface. Yeah. Any other questions?